I'm Tyler Sloan.
I'm Daniel Miller.
And I'm Cody Hyman.
And we are Team ThunderBox. The ThunderBox is a high-power motor amplifier for research applications. The 9 square inch footprint fits easily into robots and is capable of supplying nearly 10 kilowatts of power peak. That's more than 4 times the power density of other brushless DC motor amplifiers on the market. To boot, it's also about half the cost of the next best brushless DC motor amplifier on the market in that form factor. The ThunderBox engineering requirements are based around 3 main areas. The first being that it can actually drive motors at high power. That being because the ThunderBox is a high-powered motor amplifier. That's why about a third of our engineering requirements are based around the input voltages which are available on Atreus, the robot which the ThunderBox is meant for, as well as that they are compatible with the motors Atreus uses, and finally that they can actually drive them at high currents. The next main area of ThunderBox engineering requirements is that they have a suitable control interface. That's so that the DRL personnel can control the ThunderBox very dynamically in their applications to not only have high currents, but also have the very specific current that they're looking for in controlling the ThunderBox. That's why the other ThunderBox engineering requirements are very much centered around its compatibility with communicating with DRL hardware. The final section of the system requirements that are connected to ThunderBox are centered around safety. That's because when you have so much power going through such expensive equipment, you want to be able to quickly shut it off when a fault condition is detected in a safe manner. So again, a good third of our engineering requirements are based wholly around making sure that when a fault condition occurs, ThunderBox shuts down in a safe manner.
The 10 ThunderBox engineering requirements that were evaluated in this course were to be able to have the ability to drive a 50 amp sinusoidal peak current through each phase of the ThunderBox, to have an RS-232 compatible debugging interface for easy debug access, to be compatible with a 24-pole 3-phase brushless DC motor as used on the Dynamic Robotics Laboratory's Atreus robot, to have a programmable over-temperature emergency stop generation that is adjustable between 80 to 150 degrees Celsius to protect in the event of an over-temperature condition, to have a fast sub-10 millisecond response time to an incoming external emergency stop signal, to fit into a small size footprint measuring only 5.75 inches by 7 inches by 3.8 inches, to have a 30 to 55 volt DC input supply voltage range and only one input supply, to be able to have an over and under voltage detection circuit that can respond to an excess or under voltage condition within 10 milliseconds, to have a USB reprogramming interface to reflash firmware onto the ThunderBox, and lastly, to have a hardware SPI interface to allow the ThunderBox to communicate with Dynamic Robotics Laboratory hardware, such as their Medulla processor interface. All of these engineering requirements and more were met during the course of this development cycle. Now, let's go over the ThunderBox systems in a diagram format.
This diagram shows the general structure of the ThunderBox module and its environment. The ThunderBox module itself in the center consists of a single printed circuit board with a communication interface, a 3-phase motor controller connected to a 3-phase inverter, and a heat spreader and mounting plate. Around the module are the user systems, including a 3-phase brushless motor with velocity and position feedback, an external emergency stop system, an external communication interface, and a user PC for configuration. In order to drive a motor, the ThunderBox includes a high-performance 3-phase inverter constructed from MOSFETs. This inverter switches current into the 3-phase motor that's shown, and also senses the current that is being driven into the motor for control. The 3-phase inverter is controlled by a 3-phase motor controller. This motor controller is centered around a motion control processor from Performance Motion Devices. It generates PWM signals to control the inverter bridge, and also receives feedback in terms of motor current from the inverter, and also through motor sensors such as a quadrature encoder and Hall phase position sensors. The motor controller is also responsible for low-level commutation, that is, to make the motor spin by changing current directions, which it does sinusoidally, and also to control parameters of motion such as the torque of the motor and its velocity. The ThunderBox also includes a combined heat spreader and mounting plate machined from a single piece of aluminum. This part allows for removal of heat from the three-phase inverter generated while driving the motor, and also provides an easy mounting point to the user's robot. The ThunderBox communication interface coordinates communication between the user systems via RS-232 or SPI, and the rest of the ThunderBox systems such as the three-phase controller and onboard sensors. To protect both the ThunderBox and the user system, the communication interface coordinates emergency stop communication between the ThunderBox and an external system. The external emergency stop bus is notified of internal faults on the ThunderBox, and the ThunderBox may also read in external faults and shut itself down to protect itself. The ThunderBox package also includes a PyQt-based configuration GUI. This program allows users to plug into the ThunderBox via the communication interface and reconfigure parameters of the ThunderBox, such as motor loop constants and the number of encoder counts per revolution. Under normal operation, communication interface would receive commands over SPI from an external user board, such as Dynamic Robotics Laboratories Medulla. Motor commands, as well as setup and feedback data, will be transferred back and forth between these two systems via the SPI link.
Now that you know how the ThunderBox works, it's time for a demonstration.
Today, we're going to discuss the process of setting up the ThunderBox motor amplifier with a new motor for the first time. We're also going to discuss some of the critical engineering requirements that you should consider in your application. If we take a brief look at our test setup here, you can see that we have the ThunderBox motor amplifier mounted to a thermal interface. It's a fairly large thermal interface because the heat spreader that it's equipped with is not designed to dissipate its full output power. It needs to be connected to another thermal interface that's capable of that. You can see that we have used thermal grease to reduce the thermal impedance between the heat spreader and the thermal interface on our test setup. Additionally, we also have 13,000 microfarads of capacitance connected directly at the motor amplifier's power input. This is necessary because the amplifier draws large transient currents when commutating a motor. If your power supply has long leads or low output capacitance, it's necessary to supply this. Our motor here is a 24-pole, sinusoidally wound, three-phase brushless DC motor. It's equipped with 120-degree Hall sensor outputs, as well as a 3500 line per revolution encoder. We're decoding that in quadrature, so we have 4 times 3500 lines per revolution. Since it's sinusoidally wound, we'll be using sinusoidal commutation. In order to do this, it's necessary to provide Hall feedback so that commutation can be initialized, and encoder feedback so that the PWM can be modulated within an electrical cycle. If you're using a trapezoidally wound motor and you would like to use trapezoidal commutation, it's not necessary to provide the encoder feedback. We also need to connect the three-phase output of the motor amplifier to the windings of the motor. It's important to match the windings of the motor to the correct phases on the amplifier so that commutation will be successful. The motor amplifier can be configured with 2 interfaces. One is an RS-232 interface designed for low-speed control and debugging, and the other is an SPI interface designed for high-speed 1 kHz control loops. You may choose to use either on your initial startup. However, it's recommended that you use RS-232 so that you don't have to write any special software or firmware to communicate with the device. Now that the ThunderBox has been powered on, we could take a look at the GUI. The first section of the GUI is the commutation mode selection. We can either use sinusoidal or trapezoidal commutation. Since this is a sinusoidally wound motor, we will use sinusoidal commutation. You can also select between sinusoidal field-oriented commutation or trapezoidal field-oriented commutation. It's advantageous to use field-oriented commutation if you require extra efficiency at high RPMs. We can also select a command source. We can use either the profile generator or the SPI. The SPI interface is useful if you would like to have a high-speed control loop that you control at a higher level. The profile generator is useful if you would like the ThunderBox to be in charge of creating a profile and you can supply commands at a lower frequency. Since we're doing open loop control, we will leave the closed loop selector in the off position. We also do not need to set the loop mode because we are running an open loop. The next section here are all of the ThunderBox control parameters. We will read the parameters in as a test to make sure that the ThunderBox is communicating properly. And as we see, these values have been read and they are correct. The first thing to set is the dead time, which should be set to 900 nanoseconds. The next item is phase counts. Phase counts is a number that is equal to the number of encoder counts per electrical cycle. We have a 3500 count per revolution encoder that we're decoding in quadrature, and we have 24 poles. This makes the encoder counts per cycle equal to 3500 times 4 divided by 12. That's equivalent to a number that's close to 1167. If you calculate a number that is not an integer, you can use the closest integer value. The velocity scalar and other constants that are related to control loops are not necessary to set when you're in open loop mode, so we will ignore those. It's also advantageous to set the maximum temperature to a value that is higher than the default, since it may reach 50 degrees under normal operation. I'll set it to 70. The motor limit limits the value of the command that you can send to the motor amplifier. This ultimately ends up limiting the maximum current that's deliverable to a load. We have chosen a value that is below the maximum as a safe limit for starting off. When we command the motor amplifier in open loop mode, we will be entering the command value into the motor command box. You can enter an integer between negative 32,000 and positive 32,000. So I'm going to start up the motor and we'll see how it works. So, as you can see, the motor is spinning. And if you observe the oscilloscope, you'll see that the current waveform is sinusoidal, proving that we are performing sinusoidal commutation with the customer's motor.
Now it's time for a serious talk to senior design groups next year. Now, there's three main things that the Team ThunderBox wants to let you know to keep an eye out for while you're doing senior design. The first is that you pick engineering requirements that you're able to test. It's really important that you keep in mind precisely how you're going to show Don and the senior design TAs that your design objectively meets the requirements. That's important in both the wording of the requirements and the times and the numbers that you put there, and in actually knowing, where am I going to put connections to and how am I going to scope these tests out. That's really, really important that you also, don't be too hard on yourself in requirements, and that you realize that putting your goal requirements isn't necessarily the best thing because your system is almost certainly not going to be optimal. The next thing that we really want to tell you about is to be involved in your group members' activities, because it's all group grade in senior design, and if you don't know how your partner's project is coming along or what problems they're having, you're going to have both a really hard time helping them debug if it's a week before and their part's the only part not working, and you're all going to fail that part on the group grade, and also it's going to be hard for you to spot, maybe obvious mistakes that you might make by yourself but someone else would easily catch. The final thing that we think is really important for all senior design groups to remember is that you get started early, because things are inevitably going to go wrong, and if you prototype early, you're going to catch those things. And not only that, especially for software people and sometimes other things, it's really hard to test some parts of the project if other parts of the project aren't already complete. So make sure you lay out that timeline fast and get those prototypes out early so you can make sure you see those things head down the line and you're not staying up all night the week before checkoff. Keep those things in mind so that you don't make the same mistakes Team ThunderBox did.
That concludes the product demonstration for the Dynamic Robotics Laboratory's ThunderBox module. a 3-phase brushless motor controller capable of providing very high currents at moderate voltages for robotics applications. Thanks for watching.